But this is to test the fact that the user really did defensive programming, put safeguards in there so that invalid situation, whether it be in this situation or whatever, that it catches it. Because that programmers, we'll see a testing principle later on, that programmers tend to test for valid conditions. And I remember when I was a programmer, I used to do that. You put a lot of testing for the valid situations. We'll talk about the psychology of that. Whereas users out there, what do? They can put invalid ones because they may not know the system as well as you do and so forth. So that's just, the minus one there is to just to test that situation, although it's legal mathematically and so forth. And it's a form of boundary value analysis. We'll come back to that. Boundary value analysis. Look for extreme cases. That's where most of the bugs are. That's what we're going to find out.
Couldn't you also test them for blanks? Say someone might
Sure.
be putting two values?
Sure, that's another one in there. There's probably, you could go on and come up with 100 test cases.
Yeah, there's quite a few in here.
Yeah. Blanks or special characters. Where does it stop? Dollar sign, yeah, sure. So it's not totally exhaustive here. This just kind of gives a reasonable set. In fact, what you're touching on now, the principle we'll talk about, is called the economics of testing, which means that we've got to be very careful in testing. You can't be a hero in testing. I'm anticipating what to say here, but we'll come right back to that. We're going to talk about the economics of testing. When do you stop? Very important consideration. How do you know when to stop, and what is reasonable that you feel that you've done well enough? We'll look at that. I think what you'll find is a lot of the methodologies I talk about and everything will capture most of the bugs if you apply them. So let's go into the introduction section. The subtop broad line here is we're going to look at life cycle, look at some terminology, look at the definition of testing, and some other things here, some testing principles. A lot of them relate to like your point and the thing about like when you stop economics of testing. So if you look from a life cycle point of view, like the traditional phases involve requirements, external planning for design, program development, testing, delivery. What you see traditionally is not enough time to spend up here like a definition. There is some attention to use concepts like structured analysis more and more, but you know what I'm finding? And I teach one of the courses I teach is structured analysis. I'm finding that people say they use structured analysis and they spend a lot of time up here. But you should spend more time up here. They say they know, but when we get into the classroom and everything, we find out that they really don't, And like how many people here use structured analysis as a technique for development? How do you define your requirements of the system you're going to build? In what form? Somebody says, here's a system I'd like you to develop. How do you capture like the requirements of what that system will be? Okay, so you mean structured analysis, data flow diagrams? Okay, that sort of thing. So
Using more function modeling than that kind of.
okay. I still think that there's a lot of room to be improved up here. Industry-wide, we need to spend more attention up here, more education, and so forth. There is a direct connection between this and testing, by the way, right? Because that's the what. You say, hey, I want to do this, develop a system and so forth and everything. When you get on to testing of the actual finished product, it's this. That's why I like both ends, the front end and the back end, because there's a direct relationship between the two. And then consistent. We don't spend enough time, 10%. Let's move it up more and more, and maybe I'll even update this chart and show it, probably higher. External design, not enough time. Again, these are just rough figures of merit and percentages. Internal design, still not enough. A lot of time here in development coding, right? We can spend a lot of time and allocate a lot of time for developing the thing and reworking the thing, right? A lot of time in here is because you're rippling back and forth because of something that wasn't set up here. And you're backtracking, which can be wasted. Then we get into testing, we do allow a lot of time. Like 30 to 50% of the time allocated to testing. It's an enormous amount of time, yet ironically we don't have enough education, people don't really know how to test properly and so forth. Too bad. I think there are methodologies and so forth, going up here to try to improve the rippling effect and everything, which should decrease this, but I still think you'll always still be testing. There is a product up in Canada called DFDM, Data Flow Diagramming Manager. Anybody familiar with that? Heard about that? The idea is to take data flow diagrams, and the diagrams themselves, you make them develop a logical model, and then you develop it into a physical model implementation, and then the implementation of your system is the data flow diagrams themselves. There's some interesting implications in that it avoids some of the internal design, the hierarchical sort of things you do in structured design and so forth. And the network itself is your implementation of it, but there's certain batch implications associated with it. And stuff like that, where you move up to here, more attention pays up here and everything, you're going to still have some down here. It may distract from here, but on a system level point of view, you're still going to have to test the system. Development like that may help you more like in unit testing. Because the point here is we spend a lot of time here, and we wait too late. As a matter of fact, also, we do all this development and say, well, let's test. I would suggest maybe a better approach would be to think about testing from day one. Have that attitude. When you're developing requirements, when you do walkthroughs and inspections and requirements and so forth, that's a form of testing. So you should think testing from day one. Every single instruction that you write, the computer, for example, development here, you should be testing the attitude. You're not just producing something, you're testing.
Very difficult to get the system include unit testing during program development.
Yeah, it's kind of meshed in here as well. This is just kind of a feel for where is effort spent, you know, and it varies from project to project. This chart kind of expands it a little bit and considers also maintenance. Okay, maintenance, 2 to 5 times the development cost down there. A lot of time spent in maintenance. Point of this chart is, like in the previous chart, it referred to like development cycle up to production. But here, I'm suggesting that you even have a testing problem in maintenance as well, because you need to test. You need to test new changes that you put into the product, and new enhancements, you know, fixes and so forth. You not only have it through the overall life cycle, you have a lot of testing involved with maintenance as well. And this also shows like a system test point of view and so forth. So again, the motivation for these 2 forals is to emphasize like the need for testing throughout the life cycle. Okay, now that we're motivated that testing is a good idea, we're going to be spending our time, let's talk a little bit about some terminology. There's often a lot of confusion about certain terminology, like the program proof. It's an attempt to find errors in the program without regard to the program's environment. That's the sort of thing involved with inductive assertions. That's the school of thought that says that I'd like to be able to prove that that program works. Like how many people here had a thing called the software engineering workshop? Had that? Heard about it? It's a workshop like in the States. It was like a 2-day class and everything, and I sat in about 4 years ago, and I hated it. Why? Because they tried to prove mathematically the program worked. They actually went through that and tried to, you know, give you the methodology to prove the program works, and I found it, even though I'm a math background, I found it very rigorous and time-consuming. It came to conclusions that this is very difficult to do. Very difficult to really prove that a program works. And since then, I understand that it's sort of dying out. That school of thought that's kind of given up, and it's really impossible to prove that something works because it's too rigorous. Instead, what they're doing is trying to concentrate on the requirements phase more rather than to prove that individual program works. Another point of view is a verification attempt to find errors, execute a program, and test a simulated environment, which is more akin to what we're talking about here. When you're going to do testing, you try to simulate a situation in specific testing. So that's more aligned to what this course is about. For validation, that means that you're going to work in a real environment. The distinction here is that's sort of simulated to try to see if it works, and that's the real, honest-to-God environment, and it would be very applicable in system testing. When you do system testing, that's real. You're really trying to work with the system as a total entity. when you're doing unit testing, often you're contriving something, you're gonna test this little module, you're gonna maybe build a driver and stubs and so forth, in a simulated environment to see that in that circumstance it works. Another terminology is called a certification, to try to certify a program, like to certify the endorsement of the correctness of a program, just as you would do with electrical equipment and so forth. I was involved in this sort of certification thing. My first job out of college and everything, I was working at like Kennedy Space Center for a General Electric Apollo project. Why? It's trying to beat the Vietnam War. The only reason, right? So I thought I'd get into that, you know, and get a deferment from the service. And that's when it was really hot down there and everything. So I joined them, and they really had certification. They tested like the Apollo for, and it was real-time programming with control data equipment. We tested online for 2 years, 24 hours a day, all the components. We hooked up like computers and wires and everything to the Apollo. Apollo was right out in the bin in there. We could see it and everything done. Just real time. That's why it was successful, because they really did a lot of testing and reliability testing. You actually would have certification. You'd run a test and you would actually sign off something like a piece of hardware and so forth. We were really applying certification. Unfortunately, I only got a year deferment, and the service finally got me, but still applying, so everything worked out. Another terminology is called like debugging, which is diagnosing and finding where the problem is and so forth. And the output of the testing process is really the input to the debugging process. Okay. Remember I talked about, a few minutes ago about your definition of testing? Please don't look ahead or the right page over there. Let's just pause for a few minutes about what we think the definition of testing is. Okay, so when you test, or your definition of it, what's going on? What do you do? So you're talking about like how, okay? So the how of testing is every condition, right? Okay. What else? When you test, what are you doing? Trying to make it fail. Okay. That's another perspective.
I think you're trying to make sure that what you're testing meets the requirements that you set for it in the first place.
What else is testing?
It means the functions can be made separate.
Okay. Any others?
I guess that it does what we think it does.
That's pretty good. Do you see any patterns here? Any commonalities between the definitions? Is there a connection between 3 and 4 and 5?
The second class.
Yeah, the bit of class. What is the class?
We'll try and prove that what it does is what it should be doing.
Yeah, I did this. Okay, does this thing do what you said it do, Yes or no? How about up here? Make it fail? Trying to break it, right? It's the opposite. Well, how about this guy?
That's method.
That sort of methodology employed with your attitude, which could this one for that one, right? With the implementation of how you do it right within it. The basic point of this discussion and so forth is to talk about the definition of testing, and we'll just say now that's a way of doing it, okay? If we concentrate on the two major schools of thought or attitude that you have when you're doing testing, which of these two do you think most programmers have? Try to do this more? That's right, industry-wide. That's the attitude, is to try to prove that it works. Okay? And most don't try to make it fail. Who do you think is right? Or is there a rightness?
I think it depends upon cost to some extent.
Sure. You always have that. You have like cost constraints involved. Welcome.
Sorry, on that cost.
Okay.
I'll talk to that.
Jim? Go Jack. We have a private joke here about
I didn't see you make that in the budget. Like, so give you a spare.
yes, fair enough. Okay. We're looking at the definition of testing to get our arms around it. We came to the conclusion of sort of two camps. One is to try to prove, make it fail. The other is to try to prove like it works. So most programmers think, and the attitude is you try to make it work, prove it, that sort of thing. And there are constraints, false constraints like involved with it. But what I'm talking about here is like attitudes. Your attitude when you go into a testing situation, and they are diametrically opposed, aren't they? If you're trying to prove something works, you're going to get a certain number of results. And a lot of it has to do with psychology. Versus trying to prove that it doesn't work, you're going to get different results. The course definition we will use, and in order to pass this course, you have to use this definition. The course definition is testing is the process of executing the program with the intent of finding errors. So we'll try to turn our way around and thinking, you think of the first piece, you try to make it fail. Okay? We'll try to, the attitude is try to break it. Right? Now, it's interesting that programmers, a lot of people have the other definition, try to prove that it works. An interesting example is like with doctors. When you go to a doctor, like he had a eye problem, both eyes shut, and you had to go to the hospital. Hit you in the eye, right? No. A branch or something hit him in his eye, and he burst him. He went to the doctor, right? Now, the doctor has the right definition of testing, right? If you went there and the doctor said to you, and here your eyes are shut and you're miserable, right? And everything, he says, well, your pancreas is okay, blood pressure's okay, your temperature's okay, and all that, and everything. I'm going to prove that you're okay, right? He doesn't want that. He wants him to work on his eye, right? He wants to find out what's wrong and zero in on that and try to diagnose, yeah, that's the problem, here's some pills to solve it. Yet programmers, we would act the other way, right? And we would try to prove that something works and so forth. And what I'm suggesting is your attitude is to try to break it, and the idea is to try to break it. It's going to be more effective. And by the way, if you have this attitude of trying to break it or prove that it's wrong and everything, you're going to really prove that it's right, aren't you? You're really going to do both. It's a question of attitude and your approach.
It was interesting yesterday actually because the lady doctor that saw me first is the one in casualty. She spent an hour on me and she did all sorts of stuff and it hurt me a lot. And after
With the eye.
Yeah.
Did zero on the eye?
She worked on me for an hour. And she said at the end of it she said, oh, I can't find anything wrong. And I thought, great, I'm out of here. Faster than lightning. And she wasn't satisfied at all. So she brought in the senior doctor or something who's actually not in casualties outside to come in, and he went through the whole thing again until he found something that was out of order.
And they had the proper definition, right? Had they said, see, you still can't open your eyes, and they said, well, you're okay, I can't find anything wrong. You passed all your tests and everything. You've been disappointed because you're in agony, you know something's wrong, you want them to break it, or break into what was wrong with it, right? They got the right attitude. But programmers, we tend to have the opposite attitude. And again, if you have the attitude of breaking them, then you're going to really prove that it works as well, but I think even more effective. Now, why do we have this attitude of the opposite view? Let's look at that for a second. Why do we tend to want to prove that it works. And it has to do with psychology. You know, we're all human. And it relates to this, and the fact that, you know, human beings tend to be highly goal-oriented, particularly with IBM. We're goal-oriented, right? Excellence. Excellence to the customer. Excellence to anything we do down here, right? Respect to the individual. Of course. But, so we're, you know, highly goal-oriented, particularly within IBM. We really are goal-oriented. Well, where's the deliverable, right? If you're goal-oriented, you're headed towards like something positive, like you want to get the final polished thing completed and so forth. It tends to make you want to have the other definition that it proves that it works. Because I'm trying to polish this thing, my goal is to make it good. I don't want to try to break the thing. And people also in general are inclined to make things rather than rip them apart. You know, testing can be a very destructive process if you have the other definition of trying to break it. For example, if you, like last night or over the weekend, you're developing or a project for years, say, your heart's in it, right? You're working on it very hard, you're polishing this thing, you know, trying to really make it a good product and everything. And then all of a sudden you're going to say, okay, now I'm going to test it and I'm going to break that thing, right? That kind of rubs you the wrong way, then it goes against the grain. It's kind of psychologically hard to break. It's almost like your child, right? How can I have the attitude I want to break it? It's difficult, right? But I claim you can overcome that. When I first saw this definition, I fought it as well. And I said, it doesn't sit right with me to try to have that attitude. But you can do that. As a matter of fact, first time I wrote a program, like after sitting in on the course and everything, the program I wrote was in like DBase 2 at that time to do course evaluations. Like when every course, when you have a course, you have evaluations, and so you get pieces of paper, right? And it used to disturb me all throughout IBM. Those pieces of paper are just like given to somebody, a manager or somebody, and you got, the class is 30, you got 30 pieces of paper, and there's no analysis of what the students are really saying and so forth. And I got sort of frustrated with that, so I wrote this program that the idea is you enter class evaluations into this DBase 2, and what it is give you frequency distribution, graphic frequency distribution for like each question, give you the mean and like standard deviation. You can see a picture of what it looks like, and it also like organizes the comments by question and also in terms of positive, negative, neutral comments and so forth. And it had some other nice options such as the database system that for a specific course you could use like a SAS approach, in that if you had one course that's done maybe 30 times during the year, you could lump them all together as one report, lumping all the instructors together as one report, like how did that course do throughout the year, or do it by instructors or sites or any combinations like that. And then we also get into comparative analysis in courses with graphics and everything. And I got more and more involved in it, and I got sort of sorry I got into it because it took a year. Hard time. You know, it's one of these deals like sort of when you get to the fifth stage where you're doing something because you really want to do it. Nobody's asking you, there's no economics and everything. You know, I got into that where I just wanted to do it. Sort of having fun and everything, but I'm sorry in a sense I've spent a lot of hours. At that time we had about 120 programmers around the world in technical education. And the idea again is we go on the road, we come to you, we come to a different site or plant and so forth, each class is cheaper than for you to go to a site. And I wrote this program and people started getting interested in it and so forth. I could start giving presentations to people. And my overall attitude was breaking from day one, because I was teaching the course and I was starting to believe what I was saying, you know. And from day one I was trying to break the damn thing. So I did a little pilot of the program. When it was like almost done, I would give it to like secretaries and so forth, and other instructors would use it. And I had some bugs at first. Okay, and people would come in and say, Bill, kind of bug your problem here. Ha ha ha. That's great. Super. Thank you very much. And it would blow them away. They said, what do you mean? Are you being smart with me? You know, I'm helping you here, and you're being smart and say thank you for a bug. I said, no, you just solved me a problem right now. You just broke it for me, and I am really glad you broke it right now rather than later on and so forth. 9 minutes. Because I had crossed over the line and had that attitude to try to break it. So I continued testing it with the mode of looking for the weird product went out. In fact, we got to Ashton Tate, we got like a license agreements, you know, for 100 of them, which IBM had to pay and everything. And I was really scared, you know, I was testing with the devil, you know. But I was testing from day one, really trying to break it. And went out there, and guess how many bugs they found? 100 instructors using it, like all the time. How many bugs? 10? 100? 0. Never found a bug. Now, I probably did a lot of exhaustive testing, like as well, but I was scared to death because I mean, you're talking reputation and stuff like that. You know, I could have gotten a maintenance nightmare. Can you imagine that? People calling up 100 people from around the world. So I was glad, and I really think that it was kind of a success story as I hit the top of definition test, trying to break it. Anytime I broke it, I felt good. You know, you can do that even though it's your own product. And the reason it's difficult is like when you hear this sort of thing, like polish and so forth. You know, but I suggest when you leave this course, if you think about it and go testing and everything, it'll even be more fun. It'll actually be fun to try to break this program that you're even working on. You can cross over that line, and you can really balance it and do a better job. Does everybody accept the definition? Okay. So let's just look at some principles now again. It's what I call testing hygiene, stuff you ought to know, just basic concepts. The necessary part of the test is definition of the expected outcome. A lot of people test and they don't indicate, you know, what should be the result. If you don't do this, if you're going to like create a test case or a test situation, you don't write down the expected result that should come out of it, what can happen? How can you get into trouble? Rick?
You get output and then you try and fit it into what should have happened.
Yeah, because you wanted to, because you have the wrong definition of testing, right? The result comes up, 13.7, right? It should be 13.9. That looks right, doesn't it? Because you wanted to, right? Last night, a fellow colleague from Canada, we were driving up to Palm Beach and stuff, and did a lot of traveling yesterday and everything. And we were starving to death about 8 o'clock last night. We were coming back looking for a seafood restaurant and couldn't find it. We wanted to see a seafood restaurant. That's what we wanted. In the area around here, we had a match, saw a billboard that said looked like the Black Shrimp Restaurant. You can see in by it says, hey, the Black Shrimp Restaurant. You know? And the symbol looks like a shrimp, you know? And it's the stump. And just the characters, if you look at it and everything, it looks like shrimp with the T and everything makes. Is anybody ready into that? And I was talking, I said, Frank, you want to stop? It's black shrimp, that's kind of weird. I'm worried, I'll try almost anything, right? Okay, let's stop, you know. We walked up there and everything, stump, you know. And he blew me away. It'd be an excellent foil for those sorts of courses that, you know, you're going to talk about psychology and communication would be excellent. Because it really looks like a Black Shrimp Restaurant. Same thing applies here, you know. You want it to be 13.7 because you're tired, you worked on it hard. 13.7 is horseshoes, that's good enough, right? The fact is 13.9, you know, I don't want to get too involved there. So you ought to write down the expected result. If you take the time to create a test and everything, write down what the expected or anticipated result should be. Because it's good for you to verify, keep yourself honest as well as other people. Other people might need to run your tests, right? And they ought to be able to look somewhere and say, yeah, 13.7 should be the answer, right? And they can look at it, yeah, it's right. That's the first principle. Another one is a program should avoid attempting to solely to hit their own program. You agree with this? Why is that true? Bias? Okay. And then it stems back again to the definition of testing. You know, even if you really have the right idea of you're trying to break something and so forth, you know, you still just, you can't kind of see something that might be there, right? So a fresh pair of eyes is what we recommend. What actually happens in IS and development groups? Do we do our own unit testing? Do you get a fresh pair of eyes to help you with that? In IS Canada, They don't, I mean, you do your own unit testing, that's it, you know. System testing, they give it like to, like the user community, and they test from that point of view. Is that the environment here? You basically do your own unit testing?
Pretty well. Programs that work pretty obviously, but, yeah, unit testing done.
Okay. So anytime you do a walkthrough, just, hey, can you look at my program, you know, that sort of thing, it will really help you to fresh pair of eyes. Similar to that is the program organization should not be the only one testing its own programs. So organizations now, right? From an organizational point of view, when you work on like a project and you finish, who tests that? Does your organization test that, or do you get somebody else like looking at it?
Outside of IBM,
I'm sorry?
meaning like an outside organisation other than IBM to test that program.
Oh, well, either way. Your organization developed it, right? Now, when you're gonna give it to somebody, right, and throw it over the wall, from an organizational point of view, does your organization test it?
Pretty well, I think, yeah.
So the idea of,
Whether we have a separate test group, which they
Yeah.
do in some IBM, no, we don't.
no separate group. Okay. And when we get to system testing, I'll show you 6 approaches to testing, like the second part of this curriculum, talking about that. You know? Sometimes you can't afford it to have a second independent test group and everything, and sometimes it's not even applicable. It really is not worth it to have another group to do that. It just depends on the situation. In the lab environment for lab products and so forth, they require, in fact, IBM requires, like in just about every case, that you have another organization called System Assurance. Another group to look over your shoulder and assure that that product is correct. Okay. Years ago, when I first started with IBM, they had a thing called product test. Has anybody heard the term product test? The name of the game today is system assurance. The distinction is, now we're talking 20 years ago. Okay? 20 years ago, there was a separate testing organization, and these people were sort of belligerent. They had lots of power, and they would come in there and they would look at your documentation, you know, with a sharp eye, and very critical, and they really slow down the process. Okay? They had a lot of power, and they would just say, stop. The product's not going on, you gotta do that. But what happened over time is it became more competitive. We get competitive pressures from our other companies against IBM and so forth. IBM realized, hey, we can't live in this environment anymore. It's a luxury to have this group saying, you didn't dot the T right here and everything, you know, stop, because they're going to lose the marketing edge. One time it was fine when we really had not much of a, like a software and hardware product like Evolve, as we mushroomed into different products and everything, we had to rethink about how we worry about quality. So they redefined it in this thing called system assurance. Now what these guys do, and it's a separate organization, they assure that it works, and they work with you. The idea, they work with you early in the game, they help you any way they can. It's the sort of thing what a manager ought to do. You know, work with, help, I need something here, okay. And that's been a lot more effective. But again, in certain organizations, you really don't need it like an independent group, you know. It depends on the situation, the answer. When we talk about system testing, I'll talk about 6 ways to do it. There's also a variation for doing it in organizations. Sure, question?
Yeah, I was going to make a comment here. In the we had the developments that set up in the UK, they had a separate group which they call product assurance, which is simply to do system tests on the product as it comes out, and that will be the same here when we're in the mission group here. So, as you say, it is a luxury, it is a bit of an overhead, but there is that effort for you to have separate systems test.
Right. Fresh pair of eyes. Doesn't matter how hard you have it, and it doesn't matter how hard you believe my definition about trying to break it and quality and stuff like that and everything. There's just something there you just cannot see. If you're locked into a certain mental attitude, it's just the old black stump. Couldn't see it. I saw what I wanted to see, you know, and that's what it was, and I'm black truck. Right?
That's right. I mean, the whole attitude of this group has to be that whatever comes over doesn't work.
Right.
And you've got to prove that it doesn't work, not prove that it does work.
these are analogous because organizations also are living organisms, right? They have their own personalities, right? And then politically, like a project manager, right? What's his or her goal in life? Work on a software development project, right? That manager, what's their goal? What are they being graded on? Dave? We all have to wake up.
The quality of the product.
Yeah, quality, and then from a project point of view, what's that manager trying to, what's he being measured on, or she? Yeah, the function, and did you get it on time, right? You got a nice little plan, it's gonna be due this time and everything, did you get it in time and cost, right? Now, that's what you're being graded on. How would you like to be, have this other organization got a lot of power over you and say, stop, I'm gonna make you miss your thing, your schedule and everything because you didn't, give you quality, right? That becomes a confrontation sort of thing, right? And, you kind of scare people, you know?
I think there is one more important point of this. Are we taking an approach to testing as a black box? Or testing is unknown. This is a separate issue. It's very difficult to do, which is true. If we now take a separate organization to come and test, we are taking a black box approach. Technically, it means somebody goes there knowing nothing about that. Keep testing for all the possibilities, things which may come or may not come out. This is one approach. This will work here. But it looks now the trend is not to do that. Because you waste unnecessary time. So you don't need to test certain things which you cannot test at all.
There's a balance, I think what you're saying, right? There's cost considerations, time and
Not
money.
only balance, I think that approach is not necessary. What is the use of testing something as a black box? I don't think we achieve anything. So it's better to know what is going to be a test, which means a separate organization cannot run through the test. Testing is very complex depending on it. So it's better that the persons who are involved will also form part of the testing. Otherwise, I don't think it will work out. Maybe a small person will come.
Learning curve, right? This other organization, what do they know? Well, we need study for months, right? You get a learning curve there, there's knowledge missing, everything there. So you need, I think what we're coming to the conclusion is sort of a balance that the developers, you know. And he said a term called black box, which we'll come back and look at. Black box versus white box. There's also a thing called gray box or window testing. When we get into system design, we're going to look at that and everything, you know, relative to that. But it's like anything in the world, there's a balance to it, you know. And I would say, like an individual programmer, first of all, the prerequisite is get the right attitude about testing. That's going to give you a quantum leap. If you really are trying to break the thing, that's your attitude, you're going to get a big zing there doing it, right? If you can get somebody else to look at it as well as colleagues, walkthroughs, inspections. Like, do you do program walkthroughs and inspections here in Australia? In general? It depends on project, but are you required to do so?
Doesn't depend on project, but it's required to do so.
Super, that's excellent. A lot of shops I've seen, it's not a requirement, some do, some don't, and everything. We'll look at that in a few minutes, you know, it's a form of testing, walkthroughs and inspections, very effective. And if you can get another group to also look for the fresh pair of eyes, you know, fine, all the better. Again, thoroughly inspect each test case. The thing that'll help you here is if you really write down what the expected results should be. Test cases must also be invalid and unexpected. That's like the minus number, like on the triangle. To a programmer, if you were saying, well, that's a triangle. Everybody knows triangles, positive numbers, and everything. You know, that's a way of thinking. You know, what it's positive. It's irrational to put a negative number in there. Well, the person is going to like use your program. They may not know that, or they just might try to trick it or whatever. You know, you got to use defensive programming. Again, programmers tend to test towards the normal case. Because, again, I think it's the wrong definition of testing. It's trying to prove it works, right? And users go out there and they put the invalid situations in there because they don't know, like, what the functionality should be and stuff. So programmers got to have that defensive posture about what their program should do when they're developing it, as is when they're testing. Another one is testing against the specifications is only half the battle. The other half is seeing whether the program does what it is not supposed to do. sort of sounds like double talk, right? But what does that mean, basically?
You often have a specification, you would run tests against it, and you're proving that the specification is working.
And it does, right?
Yeah.
It says if you do that,
So,
by God, it works, right?
what it might be doing is creating another problem somewhere else.
Yep. Yep.
And so you really need to test the program. Doesn't also cause problems where it doesn't do unexpected.
Or things like, the spec doesn't say that you shouldn't print extra payroll checks, right? It doesn't say you shouldn't, but you should have an eagle eye looking for extra stuff that really isn't in the spec. That's what that says. Look for the extra paychecks, although I wouldn't say anything. If I got an extra paycheck in the mail, I just sort of slip it into a bank account somewhere and just kind of hope it settles down, that sort of thing. Look for stuff that's not really written down there, because it's not gospel. It's just a specification that a human being wrote of the concept of what the thing should do, right? Because when somebody does it and they're going to hit that situation, everything's going to bomb. Couldn't care less what specifications you did and everything. It's going to do exactly what the program was designed for. Avoid throwaway test cases unless the program is truly a throwaway program. What's a throwaway test case? Sorry? Or it's the idea of it sitting in front of a terminal. Yeah, I'm going to test this, right? Try something. Oh, that works. Okay. Let me try something else. That works. Okay. It's called guerrilla testing, where you don't really write down what you're doing, because what you need is repeatability, right? As expensive commodities as we are here, if you take the time to test something, and you don't write down what the test is and the expected result and so forth, it's gone forever, right? You probably won't remember to recreate it, right? And certainly the next person is not going to know what you were thinking, right? And it's a waste, it can be a waste of time. On the other hand, there's a form of testing called artistic testing. What do you think artistic testing is?
We bring things up as you go.
Yeah, so, this is fine as long as you write it down, Like, when you're developing testing and so forth, you need a plan and a methodology. We're going to get into methodology. Unfortunately, what most programmers do and so forth is like trial and error, okay? You got some functionality you're going to try, and you say, okay, let's try that. Oh, let's try a combination of that. Another one of those, and there's no real methodology. The only methodology involved with the trial and error. When we get to test design, I talk about that. I'll try to give you a framework or a way of designing it maybe more effective than trial and error. But you can spend all your time in the world using these techniques, analytical techniques to come up with tests and everything, but there's still room for artistic testing, meaning that you kind of sit back and you kind of look out the window there and you say, okay, what's the weird situation? What would happen to this piece? Let your mind go and everything and try it, right? That's called artistic testing, which is fine, it's great. But allow yourself time to write down the expected results of that test and so forth. Also, do not plan the testing effort on the tacit assumption nowhere else to be found. This is your idea that you're not going to find any errors and you really tested well and everything. You probably have the wrong definition of testing. There's always going to be errors out there, except that program I did. There are errors I know about. People have called me. You can't. The answer is, let's be humble here. You can't find all the errors in the program, unless the program was maybe one statement, right? But then, like x equals a number, right? Is there a PO1? Is there a semicolon? What are the boundary values of what they could equal? Stuff like that. Even a simple program like that, there's always probably going to be errors in programs. You think in this course I'm going to give you some magic panacea and everything that you have perfect programs and everything? Forget it. What I'm going to give you is some advice and some techniques to, I think, significantly improve the probability that you're going to catch most of them. And we can't ask for much more than that, I think, This is just too many combinations. Another principle. The probability of the existence of more errors in a section of a program is proportional to the number of errors already found in that section. Meaning, if I had like a module or part of a program that I found 10 bugs in it, part A. Another part of it, which is called B, I found 2 bugs. Statistically, they have found that when you get in like a stable environment, you're sort of a steady state situation. In that case, the first section still has probably 5 times more errors than the second one. And what this basically says is bugs tend to cluster in certain areas. Why? Because the functionality is maybe complex and everything, and intrinsically there will be a lot of bugs in there. From an individual point of view, the programmer or programmers who wrote in that section might be more highly error prone than other ones. So the tip here, I think, is when you're testing and you find an area that has a lot of errors, concentrate on those areas. Even though it looks like you got them all, because you probably haven't. And what people tend to do is they say, well, gee, I found 100 in this area and everything. Found a couple over here and everything. Oh, I got them all. There's so many of them, I got all of them. The tip is to concentrate on the error-prone areas, because there's still probably more in them. Okay, the final principle is testing is extremely creative and intellectually challenging task. Why? Because you got to know the whole life cycle, don't you? You got to know about what somebody was thinking before and what the product would have been. You got to think from like a design point of view, what the thing do, You have to use your imagination and use some sort of geometry and creativity to think of what the test would be. So it's a very challenging area, and I find it interesting. In fact, I found like after taking this course, and it's been changed quite a bit, everything since I got it. But when I went back to testing it, again, after taking that course, it almost became fun to test. Almost. Testing can be laborious and everything, but I found it a lot more fun because I felt like I had control over it. I had some principles and some tools and techniques to come up with a test. I felt like more productive, So I hope, like out of this course, you get the feeling of yourself, hey, I got something here that I'm going back with, and it can help me in my career from now on. So hopefully we can achieve that. Any questions about anything we've covered thus far? This is just, up to now, it's just kind of basic stuff on motivation stuff, way of viewing it. But the key, if anything, the most important thing I think we've talked about here today is definition of testing. Because that thing can affect a lot of ways you think and productivity. So if you have no questions, we've been here like an hour and a half. Let's take a 10-minute break. Does everybody know where the coffee machines are? Somebody can show me. I know. So I'll see you in about 10 minutes, 20 up. Okay, now let's look at some different types of tests. Now again, I don't mean, before I was talking about system types of tests, like performance tests, function tests, and so forth, I don't mean that exactly here. I mean an even higher level form of testing. So this little lecture, we'll look at the life cycle, we'll look at types of testing here, and then basically talk about 2 types of testing: non-computer-based testing and computer-based testing. Most people consider testing to be computer-based testing. That is something physical, something a program, a system that exists through testing. But there's another form that's often like they like to call non-computer-based testing. They don't view it as testing. So from a traditional life cycle point of view, the actual computer-based testing occurs down here. Generally. System test here, then unit testing occurs like within here, and then the integration test is in here as well. And what I would suggest is, from a testing point of view to consider the whole life cycle as a testing phase. Put that attitude up in your mind. Always testing this phase, this one, this one, this one, this one. It doesn't have to be physical, something the program or the final product to test, to be tested. In fact, I wish they would rewrite all the directives and so forth, talk about the life cycle phases and sprinkle the word testing or two out. So this is a traditional life cycle. There's also a thing called a testing cycle, which we'll get into more like a system testing, meaning that testing has its own life cycle, which you have like requirements phase. What are the requirements we need to consider like do for testing? What is the design of our test that we're going to use to test things? From a programming point of view would be creating the test cases, executing them, and verifying them, so forth, this sort of thing. And so forth. When we get the system testing, we'll look at that and break down like each phase and show that it has its own life cycle like itself. And you need to do that, because when you get into a testing environment, you need to plan stage by stage how to plan for your testing to do it. A lot of people, just as in the development cycle, what do? They go right into programming, right? The urge to develop something as soon as possible. Same thing with testing, you fall into the same trap. You tend to go in there and they'll say, let's start testing, develop test cases and everything, and they don't spend enough time on requirements and design. How do you design for testing? After this little lecture, we're going to look into that. What are the methodologies and design considerations that one can use? So, some types of errors. Here's environmental errors, like hardware errors. We always complain with hardware people, right? In fact, so irritated yesterday. My camera, I'm down at the bridge, taking pictures of the bridge and stuff like that, and the damn camera doesn't work. It's not the battery, it's just jammed. Lights blinking, and it turns into a camera shot, don't know what it is. Can't take pictures, I gotta solve that. It's got a hardware problem with my camera, it's really busted. Right? Or you have hardware constraints, right? You have hardware constraints that can inhibit the software, right? It used to be like storage and stuff like that, although we're overcoming that, right? There's more storage and more data feeds. Those are considerations like that are going away. Could have language errors with the compiler itself could have a bug in it. DL1 have a bug in it, right? Here you're trying to use this language that's got a bug in it itself, right? Which compounds the problems you're working on. System software errors like operating system like yours, they can be very hairy. That often involve time, right? Time limits, control blocks, during this state with storage and so forth, and they're often very difficult to find out where the problem is. And last one, the old famous GIGO, right? Garbage in, garbage out, and the entry errors. Software errors, you can get errors in modeling or definition errors. These two are often related. By modeling, I mean things like structure and analysis, tools like that. You have errors in here. If you have errors here in the life cycle, it's going to ripple down out, right? Could be design errors, not enough design, wrong design, coding errors. A lot of attitude is that we have a lot of bugs in coding, right? Where do you think most of the bugs are when we make mistakes in the life cycle? Coding? Or up here? Where do you think most of the bugs are? Coding?
There's more in coding, but if there are errors earlier, they're more expensive. One error up in modeling could cost the same as 100 errors.
Right. Numerically, there are maybe more coding errors, although we do a darn good job. Programmers that program. We code good. We do a damn good job. Compared to the number of possible scenarios and situations that we do a very good job as programmers, and it's taken us years to recognize we've got a problem with this end up here. If you look at the history of computer science, we came up with the hardware, came up with like machine language. Anybody ever program machine language, ones and zeros? For a living or part of a Yeah, that's very difficult, right? Because you can't see the problem. They've got a assembly language that thought we had the world on fire, right? How many have written in like an assembly language? was kind of fun too, right? And then we created like a higher level language, right? Fortran, I guess the first came out and so forth. Hey, this is, hey, you really got power, right? And all the time we were studying the really programming phase, right? In there for years, right? Then a thing called structured programming came out, right? What year? 69, I think, Dijkstra from the Netherlands, around that area. That wasn't long ago, right? He said, let's stop writing spaghetti program, you know, let's use three constructs. You can write any program with three constructs. No more spaghetti programming. And I remember I was a programmer back there, and at first I was kind of like, constraints in my creativity, right? And it took a little bit of time for programmers to say, yeah, okay, well, why about that? I said, great. Okay, so now we mastered the coding phase. Then what did we do? What was the next breakthrough in computer science that came out? In the design area, structured design, those techniques came out because they said, hey, we've improved our tools in the programming phase and everything, but we've got a problem in development cycle. These design considerations up there that we screwed up, you got to do that. So we started working back in the development cycle. So in the 70s, we came up with the early 70s design techniques, and then what happened? Then we went to requirements, right? Data flow diagrams came out. When did data flow diagrams come out? For example? Yeah, the end of the 70s, right? 10 years ago, that wasn't long, right? And we've been moving backwards, in the development cycle. Got to concentrate on things up here. There's a connection down here that's going to ripple all the way down. Documentation errors as well, that can be there. You could have a perfect system, but if your documentation doesn't match your system, you have a lot of problems. So let's look at now non-computer-based versus computer-based programming for systems. For a long time there, we thought the program should be written solely for machine execution and everything. These programmers were kind of like strange people in cubicles and offices. They kind of came up with a product, God knows how they do it, but boy, they're really neat people, right? We really need them and give them a lot of money and stuff like that. And then when Weinberg wrote the book, The Psychology of Computer Programming, he said, hey, that's the wrong attitude. Program should be read by people, right? Make it readable to people, right? So he made a big change like in the 70s, because he was aware of the fact that human processes tend to be more effective than computer-based testing. Computer-based testing means you test the actual, can this copy command work? Does it work on the computer? Yes or no, right? With all the variations. But he was aware that if you put people into a room and discuss this copy program that we're doing, or the design of it, the requirements and the coding and so forth, you're going to find a lot of things that you wouldn't have on the computer. It's a lot more effective. Therefore, when you write programs in the first place, they ought to be readable to people. Or change the attitude to be this. So two forms of non-computer based testing, and most people, 99.9 people don't view walkthroughs and inspections as being a testing methodology. They are structured walkthroughs. It's a walkthrough. It's not testing. We're doing a walkthrough, not testing. We're doing an inspection. We're not testing. But what I would suggest is you are testing, and it's a very effective form of non-computer based testing. What's the basic difference between these two? You said here you do like walkthroughs. How many do walkthroughs, structured walkthroughs? How many do inspections? Does anybody know the distinction between the two?
Walkthrough involves a group, right? The inspection involves giving it to someone else. Yes, checks it.
We'll go over that. The basic idea of the structured walkthrough would be anywhere in the life cycle action. People get together, and then this term here says structured. A walkthrough by itself could be something informal like, hey, in here and let's look at this thing I'm working on. Can you give me your opinion, something like that, kind of informal, from perspective, up to structured walkthrough. It's well defined what's going to happen. Did people get the materials ahead of time? And the ground rules are set. You have people monitoring it, controlling it, and so forth, as well, structured, time, plan, and so forth, which could occur anywhere in the life cycle. The meeting of like people like get together. Now, inspection, on the other hand, relates back to the life cycle. It's a very rigid technique whereby you do an inspection for this phase, and you have an entrance criteria and an exit criteria. And the idea is you can't go to the next phase, like the design phase, until you have an inspection and pass the inspection. It usually relates to lab-oriented projects, okay? And it's required by like corporate that they go through the inspections. You can't go on. It's a good idea, right? That's trying to hit off the idea of the Ripley inspection, right? It's people getting together, very regimented, checklists involved. You have moderators. You get presenter moderators and so forth, and they gotta pass the test to go on to the next phase. That's the idea. That's the biggest difference between the two. So a walkthrough is like a review of some sort of work product. Again, it has the right definition of testing defined areas, 4 to 6 people, fairly small little group. A presenter. I'm going to do a walkthrough of my program, like a code walkthrough. That's the form of it. Okay, I do this at this point. I do this. Any questions? Bill, why did you do it that way? Because that's going to cause some problems somewhere else. Hey, you're right. Thank you. Coordinator. Coordinator, that kind of sets up the meeting, and a lot of administrative things like involved with it. Okay? And then other developments, probably like on the same team, related kin. You get detailed comments and maybe a management summary. Now, do you think a manager should be at a walkthrough and inspection? Should they participate during the meeting? Why?
Because manager has another responsibility other than project is employee's responsibility. And the employees might feel that responsibility in reviewing the employees' quality of work rather than just the work.
Right.
As opposed to the
It can be very threatening because the presenter's sitting there around managers evaluate, that sort of thing. You get into game effects too. Like somebody there could be asking questions to show what they know, not to really be productive, but show what they know to the manager relative to the picture there. I taught a
People
class.
do that anyway, regardless of whether
Yeah. It's just indirectly, like, hey, this turkey here, that sort of thing. But you tend to not want to have like managers like these meetings. I taught a class about 6 months ago where there was a manager there, and I definitely saw the influence because the people that worked for the individual were there as well, and you could just see it as a group. And it's not productive because the idea is to find errors, not even games and stuff like that. Television. And you might come up with this, management summary. Well, how did it go? Not just point anything. How did it go? Are we on track? That sort of thing. An inspection, on the other hand, is a lot more formal. The formal examination of the work product over the life cycle. Each phase you must do an inspection. And it involves checklists. People have checklists in front of them. They're looking for things. Historically, in the past, they found certain types of errors like in here. Okay? Or here. And everybody there in the room has a checklist of those things that they've done in the past. And when the presenter is presenting, they're looking through the checklist and saying, yeah, how about that case though? You screwed up again. A lot more formal. And the idea is quality. 4 to 6 people, there can be more. These groups tend to be a little larger. A moderator, what does a moderator do?
In case there's a conflict, somebody has to moderate.
Right, somebody controlling, right? Because you can get find errors, right? And improve quality. There's a tendency to try to solve the problem right then, right? Oh, we have a problem here. Okay, well, why don't you do it this way? If you do it that way, that's what's going to happen, and so forth, right? And the idea of like inspecting walkthroughs is identify problems. You should not at that time do that. You get into feuds like this or arguments or stuff like that. Moderator says, "Hey, stop! We're off track. Let's get back on." You know, you need somebody separate from the person presenting. You have a designer, coder, and maybe somebody from the testing area, maybe somebody maintenance area, maybe somebody from performance analysis, right? It depends. The dependency lies in the nature of the project, right? If you have a real-time system that has performance characteristics intrinsic to the system and everything, you might want to deliberately get somebody from performance sitting there during walking through the test and so forth. So the audience here depends on the nature of the project. So when you get detailed summary reports, like what types of errors, what types of errors and where are they? Detailed reports, right? And what you do is after this life cycle, you got statistics and so forth. When you get to the next life cycle and everything, you make it better the next time, right? Because it's been shown in the past that you have a certain number of errors like here, that reflects upon the way you do things for this life cycle, and maybe you should spend more time here. So this is good feedback when you do it, back to the next time you do it. But they have courses in this that you can take. Walkthroughs, inspection, even have a course on moderator training, how to be a good moderator and control psychology and so forth. Okay, so that's non-computer-based testing. Computer-based testing has to do with the execution of real things. And this is what most people associate with testing. This chart kind of shows a guideline of the different types of tests that one might do. First is unit testing, because that's the lowest element of the thing you're going to test. And then we get these little elements tested. The idea is to do integration testing, putting them together, test the inner component, the parameters and so forth. See if they fit together, you know? Then when you get to that, you can do like function testing, test the functionality. And some people blend these two together, function testing and like system testing. I'll just have, for convenience, I'll split it out. In system testing, what is system test? When you say, let's do a system test next week, what are you doing? You've added more and more here, unit of works. Integrates together. Functionality is there. What do we mean by system testing? What's going on? Conditions for what?
Like the manufacturing one.
Right.
Upstream, downstream system connection.
Right.
It's a real thing. How you really use.
Yep. Depends on the project. It goes back to the objectives of the system. It's one or more tests from a system level point of view that you're going to use to prove that the system doesn't work. Right? Except that definition here as well. And then you could have like an acceptance test here. What's an acceptance test? Do you have acceptance tests here? Formally defined? What do you do in an acceptance test? What's the difference between an acceptance test and a system test?
The previously established set of conditions that the user will accept the system on and sign it off on.
Right. And why would one want to do that? You've been through all this, right? Why would you want to do it again? Because, by the way, most of the tests in here are probably subsets of tests done here. Usually. Although you can have some other tests thrown in like as well. But why do you want to do another test called acceptance test? What's the motivation? I'm sorry? Couldn't we have done that here? We just extend the length of time, right?
I think to just directly user can, that is where he accepts it.
Yeah, this
We-
last
we-
sign off,
We-
sort of
we test only
psychological.
for those points.
Yeah.
In system test, probably we may test for some of things, for example, volume of transactions. User is not interested whether the system process 1,000
Right.
transaction or 10,000 transactions. He's not interested.
Yeah.
He must know that this transaction should be processed.
Yeah. And there's a deliberate, maybe it's a banking situation, or sitting at the teller machine, I've gotta be able to, this one is true to my heart. This thing has gotta work. Got to work. And if you get that to work, I'll buy you a seat. So it's partly psychological, that I know you've done all this stuff. We'll do one more, and if it still works, hey, I'll buy it, I'll spend the money, right? The other key reason for an acceptance test is what? So psychological, partly it's the last test. What's another good reason for an acceptance test?
It is user comfort.
Okay.
There's a business case as well.
Okay.
Part of the motivation is to make sure that if we run these cases through and the user accepts it and we've spent this much, then that's the final
Right.
review of the business case to say whether it's worthwhile or not.
Right. Final kind of sanity test and everything, right? It's a contractual deal again. Thing I'm getting at also is the fact that, hey, when you did all these tests and everything up here, you probably found some errors, right? You went back and fixed them, right? How does that user know down here that really the thing is stable, right? That's another last check to say, hey, is the thing really stable? Given that you did find a lot of errors and everything, that's a good idea. Because if you don't want to, somebody spend a lot of money on a system and everything, you know, if you just say to him, well, we pass all the tests, everything runs and everything, he knows as well as you know that you went back and modified something, right? How does he or she know, the user, that you went back and made it correct? Do one more test with some very specific test pieces in there relative to your requirements and everything. Good idea.
You wouldn't complete the system test. If you found an error during the system test, you wouldn't complete it until you approve the test test.
You mean
Now,
down
what-
here?
No, system test. If you found an error, that the user had an error during the system test, you wouldn't say system test until that error had been moved.
Yep. But the user may not be involved with every one of those. The idea, you know. So there's some confidence like involved there. Did you really test that and so forth? You know.
The other point is how many other functions did it affect?
Yes.
I disagree. The user is involved all the way through system testing. We need to do that, and we do retest that function to make sure that the user's happy once we change it. But there may be 50 other test cases that have gone before, and we may not necessarily rerun all those through. And we did it in Magic. We tested fine. Tested finally. What we did in acceptance test was we also ran it against some very light files, very light files. So in other words, the system test we ran it against a file that had, say, one go to GitHub, but 20 entries on it. In production, it would have 150. So we whacked in 150 against the acceptance test. In other words, we tried to put in as many simulated production files as absolutely possible. So we didn't have the facilities to do a system test, but we could get it for a short period of time in acceptance test to run through the final stage. So it's sort of like a stress test, so it's a volume test maybe, if you want to call it.
Right. When we get into system testing, we do look inside of here, look at the different type of tests. We'll talk about some strategy, like about installation. Well, how do you install, like in parallel and stuff like that? You know, how do you do the different like tests within here? How do you plan the relationship between that and that? You know, planning considerations. We'll look at what each test. And then installing the test. Can you install it? Right? You ever had a system that works fine here in the lab and everything? Go out there and everything? Doesn't work? Can't install it. I used to be involved like with NASA when I worked with another company called Radiation. We did some real-time satellite work and everything, and I've had occasions where seen it at plant where we're working. Works fine. But you go out there, you know, in like a different environment, doesn't work on this system. We used to work with paper tape. That's how it started out, paper tape. We used to get it was assembly language programming. We used to get our symbolic listings source off of paper tape. It used to take 10 characters per second to print, you know. you didn't get these nice things in bins and everything, you know, that you get from high-speed printers you do today and everything. You sit there and wait for the self-tape for an hour to print it with some like this, right? In some ways, I think in the olden days there, we were more maybe careful in some ways, because if you made a mistake, you gotta do it again, right? So you really tried to, you know, save time. Also, the object would come out like in paper tape. When we went out to the field and tried to install it like with the paper tape, first time we went out, we couldn't read it through the reader because it wasn't adjusted to where ours was. We had to go home. You got to do that. When you get into the environment, make sure the thing in the environment, whether it's on a boat or somebody else's installation, and the thing works. Matter of fact, right now, there's a test system called Depop. Anybody heard of that? There's a development kind of there's some work for it as I did.
I turned up this morning and working on baseball.
Is that right? Because, well, that's probably they know I'm here, right? From Canada? Or,
No.
yeah, because that Depop team was down there a couple of weeks ago, I understand, they're in that phase, right? Installation phase, testing out here.
Yeah, I'm not sure. The whole group being set up as far as I know.
They're bringing in additives to modify it.
Yeah, because up in Canada, the software might run, it's cold and stuff, right? Down here, you know, makes it warm, everything, you know, it works, stuff like that. Environmental situation, you know, whatever, you know, you gotta do all these phases and we'll come back. This course really is this and this. It's 2.5 days, we'll talk about integrate tool, but this is the rest of the course. Give you a broad spectrum of all the different types of tests. Everything you want to know about system testing, we're afraid to ask. Now, here's kind of an interesting chart that just shows sort of a generic relationship between the different types of tests and documents in the development cycle phase. So with each test here, if somebody said, next Monday morning you are going to be in system testing, that group, for 3 months. What you need to know is if that's your job and everything, what document you need to go to that will be the basis of developing the tests, right? In that case would be the objectives. Each test within here that you define is based upon what are the objectives of the system that you're going to develop like in the first place. Like a real-time, high-response, real-time computer application has certain objectives, right? Response time, stuff like that, and everything, as opposed to a system that would, like, say, batch to print our payroll check sometime Sunday night, 3 o'clock in the morning. Couldn't care less if it does it at 2 or 3, as long as it's done by Monday morning, right? That's the objectives of that system. So somewhere when you were developing the system, somebody wrote some objectives or document, some kind of document that's defining, well, why are we doing this? What are the things we want to get out of it? Do you have a document here that refers to objectives? Is it called objectives? Maybe called something else, but it's a document defining why we're building the system. What's it called? Like an objectives section within there? And that's very important. Because as a tester, that's the thing you go to. You say, what are the objectives of the system? Please explain to me, show me where they are. Now, based upon that, I can develop and design the tests that will be involved. Okay? And other things like unit testing, we'll go back to the detailed design specification. For example, detailed design when you did pseudocoding, detailed design like that, and everything, that could be the basis of the testing you do here like unit testing. So each test has a relevant document to go to, and as a tester, you need to say, where's the document? But that's how I know how to think about it. An interesting phenomenon here, you have a backwards relationship. You build or do tests in this order, but it's in reverse order of the development cycle itself. Kind of interesting, you know? The fact that unit testing relates to design and requirements really goes back to acceptance. There's just reverse order. It's an interesting phenomenon.
When they meet.
Yeah, the meet in the middle and there's an explosion, right?
Because
It just kind of goes like this and they never meet. This is just kind of a perspective thing to see the test. Again, in this course we're going to talk this, and then the other half is really not. Any questions about anything in addition to talk about? jump feet first into something that will be fun and dear to your heart, Scott. This design, yeah.
Is a quantitative measure to show in any development what is the productivity contribution by non-computers and computers, how much really it came out from the previous example.
I've never really seen any quantitative studies that's been done on that, but I think it's significant if done correctly. If you do like walkthroughs and inspections, I think it's just like by analogy to the life cycle. The fact that you do things earlier and everything, it's going to have like the rippling effect is going to be decreased. I think like walkthroughs and inspections, it's cheap. You know, it's real cheap to be in a room to find errors right then. You know, I have no idea that quantitatively, you know, the figure merits of comparing the two and everything, but I would suspect you get more for your money on non-computer based testing.
Because I can understand the contribution by inspection and this is practical and walk. Really achieve something.
I think
Most
so.
of the times I have seen in doctors, it's a very high level discussion. People don't have full understanding of what is being discussed because they are not aware. They are all from different areas. So they just come to see how the standard they are going through the class, path.
That relates, I think, to the nature of the meeting. You know, you could have a structured walkthrough that really is structured, it's well organized, methodical, one after another, defined and so forth. You know, versus one that could be informal. You know, I think it depends upon the person that's controlling the the testing manager and everything. You know, good testing manager would make a good instruction, make it very clear what's going to occur, when, where, how. People have all their materials beforehand. You know. They come prepared, ready, you know, versus, hey, can you come on in, look at something? But in any case, I think it's a really good idea. We ought to do more of that. Walkthroughs and inspections, but make it a little bit more structured.
In that book, Art of Software Testing, there are some figures in there. I've got one upstairs, I'll get it at lunchtime. There are some figures about walkthroughs. I don't know them off the top of my head, but it will answer your question. How true they are. They're from the States between 79 and 81 time frame, so, but I'll get some for you. I think we use around about 5 to 10% of the development cost is allocated to walkthroughs across the life cycle. So that gives you an idea of the time that's involved. I think one of the keys to walkthrough success is appointing individuals to do specific jobs in the walkthrough. So you don't invite someone to just say, oh, have a look. And you say, I want you to look at the standards, I want you to look at the database design area or the calls or whatever, I want you to look at the structure, the program. Tell people to hone in on something specific and come prepared.
They really come to structure work.
Yeah. There's a lot of leeway. Some people say they use structured walkthroughs and
Do they really?
do they really, you know, so if you've got a lot of people sitting there just waffling on, I think that's not really what a structured walkthrough is about. That's just education.
Yeah.
So it's like deliverables is what you mean, you know?
Yeah.
You're responsible for that. That's great. Okay, so now I claim that general programmers don't know how to design test cases or plan for design. It's basically trial and error. And we do a pretty good job given that knowledge. But there are some techniques that you can help you really do a better job in testing. And that's what we're going to look at now. Mini top of outline would be, you know, looking at what is the test case itself, some views of systems, getting the black box, white box point views. And then we'll look at the techniques. White box, we'll do lots of exercises. We'll look at black box, we'll do lots of exercises. And the final workshop and everything is based upon, I'm going to give you like a little specification, and it'll seem like, hey, I can do that in half an hour, right? I don't think so. To do it thoroughly, it takes 3 to 4 hours. And you'd be sitting there thinking, well, we use this methodology, and we're going to consider this boundary situation. You really can feel it, you know? When you leave here, you'll be able to do that again. And that's the idea of these classes, really. When you leave here, you do it. You have to be working knowledge, okay? That's why I put it at the end, okay? And what we'll have is like presentations there, class day. So it looks like maybe 2 groups, depends on how many are here at that time. I had a lot of fun doing that. It's also kind of helps me days like this, I got 5 to go, and you're breaking in. And we have a good time. We'll make it informal. We'll be another classroom there, but we can maybe find some breakout rooms, and each group come up with their presentation. Okay, let's just talk basics now. What is a test case? A test case is a specific set of data along with expected results for a particular test objective. Okay, so it's data. Data test a certain test objective, and there's an associated expected results. Remember the principle? You got to do that. You got to write down what's expected. What's the data? What's the objective? And what's the expected result? 13.7. That's what I want to get out of it. Some other things you can put it on is like identification. In fact, when I get later on, like in system level course, I'm going to give you examples of documentation you can use, right? How do you document a test case, right? How do you do it? I'll show you examples like that of a form that one could use to fill out test cases if you want to. All sorts of test documents that will kind of tie this together. You could identify it, right? What's the name of the test case? I highly recommend that you use self-defining documentation for the test case itself. Like on the test case library, if it's like maybe 10 characters long and everything, use the name of the test case to identify the type of test that's involved. And maybe the part of the systems that involved, maybe the date that's involved, and also the programmer, such that somebody can look at that name and say, oh yeah, that's the utilities. That's the utility test case that works like in this area, and it's self-documented. Very important. The other thing that's important in test case development or anything else is standards. Be consistent with your standard naming conventions, stuff like that. What's the purpose of the test case? What's the data set up? Amount of tape, what you got to do is set up the data. What's the data input to it? What's the expected output? And what's other requirements that's involved? And I'll show you a specific example of what the documentation could look like for test cases. Now let's back off a little bit and just talk in general about what is a system. The reason I'm doing that is just motivation for the difference between black box and white box, what it is. So any system, a traffic system out here, Sydney, a computer system, a biological system, whatever. It's a collection of elements and components, with characteristics and functionality. Like his eye, when he has eye trouble, well, one of his functions of his eye, was screwed up yesterday, right? He had certain characteristics like he ought to be able to see, right? But it closed up. That component of his system was changed. And the relationship between the elements in it, and there's some common objective. All systems are like this. And for the system involved, with the elements inside, there's usually an arbitrary boundary between that and the outside world of where it resides. And what is it? It could be a subsystem within like the larger system and everything, but within its world, there's usually an artificial or arbitrary boundary there. Okay, so there's a connection between this and that, whatever, however you define it. And this is the point I just stated, that each subsystem within a system could be a system within itself. So we're kind of talking set theory here, In fact, testing methodologies and everything lends itself nicely to set sort of theory. Okay? And we'll look at a thing called equivalence class partitioning, which is what I think that's like a set theory sort of approach to testing. Okay, given that we understand what the system now, there's like two views. One is the black box view, which he mentioned. And then there's a white box view. Black box means I'm looking at your system from the outside. Couldn't care less what happens inside. Don't want to know. Analogy would be I'm driving a car. I don't have to know how the engine works, or the transmission or anything, right? I just need to be able to get in the car, turn the key and everything, and do stuff like that. I do have a little trouble myself driving on the left and stuff like that. I took a cab here today. I'm trying to wean myself off that run a car, So I've got a black box problem with driving because I'm not used to that. Frank, with he's doing good. He's gotten over that. And he's doing good, right? black box view of anything is I couldn't care less about how you do it internally. I care about the external, right? I don't ever have to lift up the hood of the car to drive it. White box is the inside view of the system. I care how it internally works. I want to lift up the hood. I'm going to check the oil. I'm going to check the water. I'm going to look at the fan belts, right? I'm going to understand the design and how it works in there, and I really care about it, right? Those two different distinct views of systems, and it's two different distinct views of how do you test systems. There's another form of testing, which is called gray box testing. What do you think gray box testing is? Combination of the two? Okay, from a testing point of view, you know, with black box, you just have like a specification of something indicating what the thing should do, right? You couldn't care less about how somebody did it, design or anything. You use that specification to test it, right? And you can do that, right? White boxes, you get in there, you want to know the flow paths within the program, stuff like that, and you know the internals, right? Why would somebody want a gray box view, meaning you want to kind of do both at the same time? Why would you want to know both?
So that you can concentrate on specific problem areas without worrying about the things which you've got a fair idea of how to work okay.
Okay. Couldn't you do that with just white box? You know those problems.
Yeah,
with
you could get tied down a little bit though, looking at things that are unnecessary.
Okay.
Sort of honing on a specific set of circumstances and not worry about the rest of the things. You're worried about input and output as far as everything else.
Okay. They can give you balance in other words. Let's kind of look in this world now a little bit, right? When we get to system testing, and specifically where we're going to go, is the analogy of unit testing and system testing would be unit testing is maybe 5,000 feet high. And the error is okay, you don't need oxygen masks or anything, right? It's like the old sparks, you know, flying and stuff like that. You get into system testing, you start out at maybe 15,000 feet. Right? And you still don't need oxygen masks. I think at 20,000 you start needing that, right? And in system testing, start at 15,000 all the way up to the outer space, right? With all sorts of levels of complexity and complexity involved in those different tests, right? The point is, as you get higher into system testing, things can get kind of fuzzy, right? From a system testing point of view, it says this system ought to be able to do this, but there could be some hidden agendas or something implied in what you're trying to test, or something that should be stated and it's not tested. You know, that's something we're going to hit when we hit system testing right away. We're going to start looking at these gray areas. What's some methodologies for like reading between the lines? So when you get in the stratosphere a little bit higher up there, you know, you can save a lot of time if you do gray box testing, meaning that you're looking at a specification that says it ought to do this. You say, well, let me look at the implementation of how it was done, the design. You say that, let me look over here. And I look at the design and details and everything. You can save yourself a lot of work by doing both. Because if you don't, you're on the outside and doing black box testing, and you're going to need a lot of other tests that you didn't have to do if you had looked in the architecture. And it relates to independence as well. The independence of your design and so forth. A lot of people I know do total enumeration on functions where they don't have to. You look and see the design that, hey, this really is different from that, therefore I don't have to do the combination, so I've just saved a lot of work. The idea. That's gray box testing. We'll come back more when we look at it system testing. So black box is how the system is defined functionally. Now associated with black box testing is usually the notion of exhaustive input testing. Okay, from a black box point of view, you're going to talk to the system the way you do it with like inputs and interactions, right? So one might pose the question, and you should pose the question, is it possible to use every possible input condition as a test case? In fact, we saw that earlier when we were talking about what's a test case. Every condition, that was brought up, right? Okay. Okay. That was brought up here, right? That's more than hell and everything. But related back here from a black box point of view, do you think it's possible in general to use every possible condition as a test case to test something? All valid, all possible inputs and sequence of transactions. Is that possible in general when you get a test? Can you really come up with all the inputs? How many people think you can? Yeah. Difficult, isn't it? Too many combinations, right? It's got religious overtones to me. Just the number of combinations, combinatorial mathematics and stuff like that, is just unbelievable, you know, that it just can explode without even trying. So, signal I'm saying here is if you want to do exhaustive input testing, every condition you can think of and everything, in general, forget it. Can't do it. Can't do it. Therefore, you need some sort of methodology to be as pragmatic and optimal as possible. Okay? Trial and error just doesn't cut it. But in general, that's what programmers tend to do, trial and error. They do, well, let's try this one, try that one. How do you know when you're going to stop? You need a better methodology or analytical method. And we'll look at that. The other hand, white box view. You want to look inside. And that's not necessarily a data flow diagram. Okay. With white box, you want to look inside of these components and look at the interrelationship between the components here and the relationship between the outside world, input and output point of view. So you care how it's done behaviorally. You know, you care about what is done, not and also how it's done inside, right? Now, relating to white box are these goodies in here is usually associated path testing. Alright? Because when you got a computer program, you give a certain stimulus and input to it, and it's going to go through a certain path based upon the inputs. Right? So, in this case, do you think it's in general possible to execute all paths of quote control to the program? Is that achievable? Yeah, that's just paths, you know, if this is true, if, then, else, you know. Is that in general achievable? Is it realistic to take that as a goal? Some say yeah, right? Why not, right? A module ought to fit on one page, right? How many paths could there be on one, you know, good module or a program, you know, 60 lines? How many paths could we have, right? So some are saying, yeah, maybe more achievable than the input, multiple inputs. So let's look at this case for a second. And let's see what happens if we have something like this. Suppose you have a program, this is the structure of it. You go from point A to B, and this is like a simple sequence, there's no decision. And you have like a arc like that, that's some sort of decision. So you get here, and this is like a key state, right? Where you're going to branch off here, and then you move down here. How many unique paths are there in this program? Yeah, 5. Right? 1, 2, 3, 4, 5. No problem. 5 test cases, right? I can do that, right? Of course, when I do it, I'm going to have to define my objective. I need to show what else for each test case. Yeah, and the expected result that you come out of it, right? And the objectives. Why am I doing it? Well, I'm taking this path for this particular situation, right? You find all that stuff. I can still do that. 5 I can handle. But computer programs often like to do loops, right? Yeah, that's reasonable, isn't it? In fact, computers were developed to do repetitious sort of things, right? They're good at that. We're lousy at that. We're terrible at that. I hate it myself. So that's why the computers were developed to do repetitious things. You know, like you're going through like a payroll file or something like that. You know, you want to do it over and over again and drop it. Most computers love it. So if you take the same example here and we look back once here, and then come out, how many paths are there? How many? 25. Intuitively, it seems like something else, right? First thing that jumps to your mind is how many? 10, because I'm doing it twice because I have a linear view of the thing, right? fact of the matter is, when I come through here of each path here, when I come back here, I've got 5 choices, 5 squared, right? If I loop back twice, how many paths do I have? 5 cubed, right? So it's 5, 5 to 1, 5 squared, 5 cubed, so forth, right? Suppose I do it 20 times. 20 times is reasonable, you know, algorithm, right? I'm going to loop through a table, do some numerical analysis, something like that. 20, oh, okay. Right? How many test cases would there be? For paths 10 to the 14, which is about 100 trillion. Unique paths. If I run a test case every 5 minutes, it would take me about 1 billion years. So the history of the Earth. How old is the Earth? Billion years? Or I don't know, millions? But, you know, some it's a billion years. Day one, when it was created, we're still developing test cases for this lousy program, right? We're still not done, right?
That exhaustive input. In 5 test cases, you actually did test everything else in the program.
Yeah, it would take inputs. That's true as well. But from the black box point of view, you wouldn't have had to know what would happen inside. But you're right. There's got to be some stimulus to make this jazz occur, right? But you're absolutely correct. The black box view of this would be, I don't even see this. I just know from the external requirements and everything that I can do these sorts of things to make it occur, you know? White box is, I want to know that. You know? But you're right. That surely triggers. Is this a fair example, though? You believe 100 trillion?
Most of the kids.
Right. It's good for classes and everything, right, Doug? But if there's some dependency in here with a loop like this that it really could be like entirely different, there could be something wrong with the structure, the logic. You know what I mean? Theoretically, you should do the number of tests, but probably as good programmers and everything, we really know the relationship that's coming back and everything. You know what I mean? It's like independent, not some insidious result here that ripples back that the city is there. You know what I mean? It's probably less. So it's really sort of a humbling experience what I showed you. And you should be humble. Because guess what? In general, you can't do exhaustive path testing as well just like because the input does it, right? Yet most people view, well, I could test that program. Yeah, I'm going to do all the paths, right? The assumption is I'm going to run out and do it. But the answer is, in general, you can't. It's too many of them. We've got a big problem. Therefore, given that we have a problem, given the constraints of time, cost, memory, computer time, motivation, I don't want to do that. I don't want to do 100 trillion test cases. I don't want to. Maybe 5. 10 at most. Key issue becomes in testing is your mental attitude. First of all, get the right definition of testing, and number 2 is what subset of all possible test cases have the highest probability of predicting the most error. In other words, thinking smart. Given all the tests that I could do and everything, you know, how can I really get some leverage on this sucker, right? To really get in there and, you know, look for the bugs and into the crevices, you know, look up some rocks and stuff like that, and give me a good chance at this thing. How can I do it? And at least design a minimum set of test cases to satisfy some test criterion. And other tests like as well, which you're going to need at least what is the minimum set? How do you go about thinking about what would be the minimum set to develop, and then maybe build on that relative to time that you have available. So how do you do that? Right now it's a vacuum because most programmers don't have any notion of how you'd even organize that. It's trial and error. So what I'm going to show you now is some techniques that give you a handle on that. In fact, what we've done is, I think we've come to the conclusion from an exhaustive point of view, you can't do total input and output. You can't do total path. So you need some kind of design strategy, right? Random testing is one possibility. What's random testing? What do you do with random testing?
Don't follow any sequence. Don't
Sorry?
follow any sequence. Just pick up some input. That's all.
some mechanism that uses a random number generator, you know, it has some predefined notion of the possibility of the inputs and so forth. So it takes a random number generator, it picks out a number, it divides by the number of koalas in the zoo over here, and maybe add a number of monkeys in the Toronto Zoo together to come up with that pattern. And it comes up with a test case and you run it. Do you think that's a good way of testing, random testing?
Can be if you're testing a random program. I mean, like a program that tests random numbers coming in. Maybe the only way to test it.
Mm-hmm.
I've seen
Because
that.
of the environment.
But it's very rare that you get a program like that.
There are like programs like available that, like syntax generators. You have a specification, you feed into a program, you know, like in a functional specification that shows the command and the optional parameters, you know, and that sort of stuff like that. You can feed such a thing into programs that exist and it'll generate test cases out of it randomly, or even totally in iteration if you want. Is that a good deal, you think? It's an analytical technique. That's what I call it, analytical. Or strategy. It is a strategy. Selective strategy, right? Using random. That's a good idea. If you're going to test a program, would you rely on that totally?
Doesn't concentrate the effort depending on the point. Like if you want to, you've got this range of values, you want to just randomly which test equally across the range, whereas you might want to concentrate on the boundaries. More interesting.
Yeah, beautiful. It's like the law of rare events, right? This probability distribution was probably uniformly distributed, right? And where the bugs are, and what these techniques will come out to show you, I think, is the bugs are in the weird cases, the boundaries. They're sort of like bugs, kind of hidden under the carpet right there. They're right there, right? They're not here. So if they're here, I'll find them and kill them, right? Well, we need is techniques to find these little crevices and boundary areas where they are. Statistically, if you do random, couldn't care less. We're looking on the floor. It's just looking all over the room, right? So for unit testing in general, I recommend it. Would you recommend random testing for system testing? Not a bad idea. We'll come back to see that, and I'll show you a specific example of a weird case. When I was testing a product we're working on, we would have never have found it. It's a hideous example. Never would have found it unless we had done that. Okay? System testing, not a bad idea. It's like throwing something in here, you know, stirring it up, randomly gelling, you know, and then maybe something will pop out. System, good idea. Because at the system level point of view, if you randomly do it, it's going to hit a lot of the timing conditions and stuff that you might not have experienced before. It also gives you a good feeling for the customer from acceptance point of view, because that's the sort of environment. It's random, right? Bank situation, anything can come happen. You know, somebody can come in there and you can get all sorts of patterns of weird things occurring. That's what you really want to test. So system point of view, maybe not a bad idea. Unit testing, not so cool. So therefore, in this course, what I suggest we concentrate on is what I call analytical techniques for testing, for unit testing. So that's what we're going to look at now. And we're going to do white box first, and then black box. And we're going to do like a bunch of exercises. Keep us awake, right? So the techniques associated with white box are like statement coverage, up to flow path combination coverage, which is all paths to the program, based on all conditions. And in general, of these techniques, the further you can add here, the stronger it gets. But I'll show you some exceptions as well. Okay. First white box technique is called statement coverage. And we will use the same example to study each one of these white box tests. So the idea of statement coverage is that you write test cases such that every statement in the program is executed at least once. That's the definition. In fact, I used to use this as a definition when I was a developer. They used to tell us just write enough test cases that every instruction in the program executes. Okay? That used to be the basis of it, and it's the weakest one there is. So let's take this example I have here. Give the flow chart, if you will. What I'd like you to do is come up with test cases to satisfy that definition. In other words, what I'm looking for is I wanna be able to fill out information like this. If I say like test case, I develop a table like 1, 2, 3, 4. If I say what's the value of A, B, and X, that's a test case. You give me numerical values for A, B, and X for the first test case, and the second test case will be an X here. And all you have to do to satisfy the statement is just make sure that that is executed, that are executed. Forget about anything inside, you just want it to hit the statement. Okay? So if you can spend about 2 to 3 minutes on that, come up with the input data that it would take to satisfy statement coverage. Don't make it too hard. There's a tendency to want to make it harder. Just keep it simple. It's not atomic physics either. Okay? How many test cases did it take you? One, right? I saw a couple coming up like 2 or 3. Now, who cares? A couple test cases among friends, right? The sensitivity we have to worry about is the economics, right? A certain decision that you may make might be the difference between 100 versus 200 versus 300, right? Or 1,000, 2,000, 3,000 test cases if you're careful, right? You gotta always try to do at least the minimum set to satisfy the criterion we're working with, right? So what are the numbers? What's an example?
0.
Okay, so if we walk through here, we're certainly gonna do this, right? Now where's it gonna go? Yes, right? And a bell rings immediately. Boundary value analysis, right? Anytime you do a divide, right? Shouldn't divide by 0, right? So immediately you're thinking boundary because we're all sensitized to that, right? And you make a note of what would be the value of x at that point. And then here, and what happens? We do this one, where do we go? Okay, did we satisfy statement coverage? Do we feel satisfied that it's a good deal? No, there's a certain uneasiness. Why? Well, the comparator probably caught the syntactical stuff here, right? And stuff like that. You know, it's kind of weak, but it's better than nothing. Some of the things that could go wrong is, for example, if you coded this, if this should have been or, right? Or this could have been and. it could have, depending on the data and so forth, it could have satisfied to you that it worked, but you really didn't know because you really didn't look at the conditions and so forth, right? What's the other thing that bothers you?
It makes people know.
Yeah. So intrinsically, you're wanting to execute all the branches, right? Which, by the way, is the next form of white box called decision coverage. And that test case is roughly written such that each decision has a true and false outcome at least once. So in this case, we care that everything is traversed, the yes and the no everywhere. That's all we care about, nothing else. Forget statement coverage, forget everything else. Just worry that you go that way and that way for every decision in the program. Okay? So for this one, you could spend maybe a little longer, maybe 5, 7 to 10 minutes on this one. Come up with the test case to satisfy this definition for the same example. And maybe more than one test case in this situation. But again, you always want to try to be optimal and use as minimal as you can number of test cases. Again, this is not atomic physics, right? How many test cases? Right? What's the 2 test cases?
Well, the first one will be the same as for the previous,
Which was
which was 2-0 and
alright.
and well, for the second one I had A, 0 and B next to be anything as well.
0
Yeah,
for A?
as long as it's less than 1.
0, 0,
Yeah, I had 0, 2, 2, doesn't matter.
0, 2, 2.
Yeah.
So if we follow through here, we come down here, is A greater than 1? And B was the other two, we already did this, didn't we? And down here, we already know did that. So for this test case, is A greater than 1 in that? Nope. And down here, is A equal to 2 or A x greater than 1? Does that work? For the second one, you come down here, right? You're gonna take the no because this is approved, and we get here is A, the second one here. Is A equal to 2 or x greater than 1? You go that way, right? So what do we do? Okay, and we satisfy the definition, right? Now, what do you notice? We satisfy the definition, right? What else do you notice?
All the paths are
Okay, so it satisfies statement coverage, didn't it?
all the paths weren't executed, but I think the bothers me about it is that we didn't execute all the paths. That's all the paths from top to bottom.
Right. Okay. Good. By chance, it also covers statement coverage, but that doesn't always happen. It occurs. 3 exceptions to that. One is that the program has no decision in the first place. Another one is the program has multiple entries and exits, or entries like a non-proper program and everything. The third one is asynchronous operations like PL1 beyond units. You may not get up there to execute the statement. What else can bother you about this? Which relates to what Robert suggested. If this should have been less or equal to 1 and everything, you may not catch that with this test because all you're saying is it traverses it. And particularly when it's or, this or this, either one. And if you coded this as like incorrectly, it'll satisfy it. Usually. You wouldn't know. Therefore, with the statement coverage, we sensed we needed decision coverage, right? We did, but we're still a little uneasy, right? So what do you want to do now? What sort of jumps out as maybe the next thing to do? Definition. How about conditions? Let's get inside there and look at those conditions. In this case, I put a mask in here, right? Let's get in there and look at the A equal 2. Let's look at the x greater than 1 and so forth. A little bit strong. So next definition is write enough test cases such that each condition in a decision takes on all possible outcomes of these ones. How do you do that? Well, the way you can do condition coverage is just write down all the conditions first in like a table and a list. And they would be like A is greater than 1 is a condition, right? What's another condition? A is less or equal to 1. The complement of it, right? You could just look at it, What's another one? Equal to 2. And x greater than 1, x less than 1. So the idea is with this table of conditions, and what you're doing is building like you build like a truth table actually by doing this. List down all your conditions, and then back off and write test cases that would satisfy each of these conditions and forget about everything else. Forget statement coverage, forget decision coverage and everything, and just satisfy these conditions. Come up with test cases just as we did before. Just concentrate on this. Forget statement, forget decision coverage. So again,
The execution x over A is greater than 1. X over A is
would be more black box. We're just concerned about the white box, the internal logic of how it's stated internally. So again, I'd like you to come up with A and B, yes. Where's the numbers? There could be more than two. many test cases? Oh. How many? So many. What are they?
I had 2-0 and anything correct for the first one. And I'm not sure some half 0,
I'm sorry?
half or less than 1.
I'll just say.
It depends how
We'll do
you do
numbers.
it. If you test every single, like the only one condition is not true, you don't figure out more. Some of them will just have to be true. But if you're going to test if A is greater than 1 and B is 0, then
Yeah, I see what you mean.
yeah.
The idea of condition coverage is just to worry about the individual conditions themselves.
So just for the first one, just A is greater than 1 or that whole box.
Yeah. You would, you know, if you ran these test cases through this table, you'd be able to check off each one. That's the idea. It's not worrying about the condition bitches and the thing here. When you get into worrying about the conditions and the Boolean nature of the ands, ors, and stuff like that, then you get into flow path, you know, which is the next one. So it's pretty simple. So what would be the second one? Anybody?
Use 1 and 0.
Okay? So let's play computer and see what's going to happen. Now we can ignore that. Right? We want to go over to the table here and see if it satisfies. So, A is equal to 2. That satisfies this guy here, right? And it also satisfies this one, right? This value. How about B equals 0? Satisfy that one, right? We'll bypass the any for a second. 0.5. A is less or equal to 1, so satisfy that, right? A not equal to 2 satisfies this. B equal to 1 satisfies what? This. And then x is equal to 0, which would be this case, and then any here. Probably need to make that specifically larger than 1, right? 2. Because the trick is just to come down here and you're actually testing each condition within the, okay? Now, let's go in and just observe some things in the program here, right? We can execute this statement. First test case, right? Where are we going to go? Here, right? Then where we're going to go? Yes, right? Things are looking good. We get to the second test case, and where do we go? No. And down here, where we're going to go? No, right? Okay, so what do you observe there? Just the numerical values that she chose and everything. We did that. We satisfied the definition. What else do you observe relative to what it was tested inside? Relative to the other techniques we've looked at.
Well, we did no more there than we did with the previous test.
Except we did actually test the condition. Like in the other one, I believe, the last one, the OR, this one wouldn't have gone through here necessarily to test that specific condition.
Isn't it, it seems to me it's by chance, but that you
Yeah.
execute everything, because I'm concerned about writing x is greater than 1 and x is less than or equal to 1 in a table. It's not really meaningful. Saying x is greater than 1 isn't what happens in the program. What happens in the program is a equals 2 or x over a is greater than 1.
But in the program, it checks like x greater than 1. Where is that check?
But if
Oh, you mean the fact that x is less or
this
equal to?
value changes from what the input change, this case is between when it's input and when it actually gets used in the exchange.
Oh yeah, because of stuff like this. Yeah. Okay. That's why it is limited in the extent is you're putting on the force collar just as the other ones, we looked at a specific way of looking at it. You know, at least it may dig out something in the condition here, but you're right, there's something here could additionally mask what occurs down here. So it does statement coverage, right? Because each one of these is done, right? What else does it satisfy by our definition? Decision condition, you know, decision, because we did traverse all these, right? So, in a sense, so it's satisfied, right?
But how can we make x equal to 2 there? I don't know how to use this intake test. If you take the same, if you have a statement like this, suppose I can give definitely a equal to 2 and b equal to 0. When I make a equal to 2 and b equal to 0, how can I make x also equal to 2?
Right
I
here.
don't understand what do you mean by this test case?
Yeah. Well, it's the input coming in here.
Okay.
Input values that Pete mentioned.
Yeah. Is the x is an output or an input? In the test case, a is an input.
Both. Because when you come in, well, it's a transformation. The state values of like A, B, and X and everything, they come in with the initial values of these as test cases, okay? When they come out, they're going to be transformed in some manner based upon how it's coded and the conditions within here. And then also stuff like that, you know? The thing I think you're finding about is sort of, well, gee, it bothers me. How'd you know too? Because there's some other stuff in here I don't know about. How do you know it would be effective? Right? Bothers me too. To really get into that and to like worry about all those situations, you got to go to flow path conditions, which is the next little bit stronger one. You know, I'm just saying that this definition of condition coverage is a way of viewing it. You know, and it's a definition that you just worry about with each condition in here. And there's all sorts of other things that can mask things, right? But in general, it's a little stronger than the other ones. It's just another way of like a viewing it. So it satisfies condition coverage and decision coverage, so we're feeling kind of a little better, right? I mean, at least we're, you know, a little more maybe. Supposing you had come up with a test case like as follows. Supposing we had chosen 103, 211. Okay. And let's test this again to see if it satisfies condition coverage. So if we look at here relative to the table, A equal to 1, right? So that's going to satisfy this one. It's going to satisfy that one, right? E equals 0 will satisfy this. The x equal to 3 will satisfy this guy. The A down here for this test case will satisfy this one. This one. And the D part here will satisfy that one. And the X thing here will satisfy that one. Right? So these two test cases we might have arbitrarily chosen, does it satisfy condition coverage? Yeah. So we're happy, right? But let's pass this back into the program and see what happens. So we're certainly going to execute this, right? Where are we going to go with the first test case? Where are we going to go? No? Yeah, no? And then where are we going to go? Yes or no? Okay, the next test case, we come in here. Where are we going to go? No. Here, where are we going to go? And we already stated that this one satisfies condition coverage, right? Based upon executing the conditions. But what you notice? It doesn't satisfy decision coverage, right? Only by chance, right? So you can have a possible problem with this. It's not, remember the list I had before that said usually the stronger you get, the more statement to decisions, usually stronger rule if you use it as a basis of doing testing. Here's a case where this one satisfies condition, but it doesn't satisfy decision coverage. It's just sort of a weird case. In general, it does, but you could come up with these situations. You got to be aware of. Okay. Now, if I had not had this discussion, right, I could have said, hey, what's the next stronger thing do you anticipate would have been than condition coverage by assault? The next type of testing. You might have said, oh, Bill, decision condition coverage. I insist that you traverse each one of here, and I also insist that in here you execute each condition. They're there, okay? And that's the next way of doing it. So there are no sufficient test cases that each condition and decision takes on all possible outcomes at least once, and each decision takes on all possible outcomes at least once. Written down twice. And each point of entry is invoked at least once. In other words, a proper program. It's one entry at the beginning. If we have multiple entries, they can get fuzzy. And I could have said, here's another one. Did we need to do an exercise here? If I said, here's an exercise, you know, would we have had to done an exercise to satisfy this? No, you already gave it to me, right? This one up here, remember that guy? We already did it. By chance. So when I ever teach this course, I look for it to see how you come out, okay? See if you do the one case or the other case here, and always it comes out that you do it because you sort of instinctively wanting to do the next way of doing it, like decision and condition anyhow, right? I've never seen a class that did the second one like I did, you know? It always versus decision. So we're done, right? And that's always nice. Yeah. Now, it turns out that there's another problem. You know, like in this case, it appears that it exercises all decisions and conditions, right? It's cool, strong, right? It turns out you can mask other conditions like within the system. For example, this, the compiler expansion of it, probably would look like that. It's the way the compiler expands things, right? If you say if A is greater than 1 and B is equal to 0, the compiler would probably break it down piecemeal. Do this condition, if this is true, then you do that, right? Otherwise, okay? It's the way compilers work. Okay, that makes sense. If we come back and feed that test case you gave me, which was 2, right? 202 and 0.510, and this time I'm gonna use a black foil, or else I'm gonna get screwed up. I've done that before, of course. We pass this through here, right, to the actual expansion, the pilot. What's gonna happen? We're gonna do this. Where do we go? Yes. Then where? Here. Then where? Yes. Well, for this test case, where we're going to go? Then where? Then where? Yes or no? Yeah, so the actual, like, compiler expansion, what do you notice? Oh, in this case, that did satisfy seemingly on the surface from the other flow chart, the high level. We notice in this case the actual compiler expansion. It doesn't satisfy what? Does it satisfy statement coverage? Yeah. Does it satisfy decision coverage? No. You got a problem, right? Didn't do this or that. Okay? Which leads to the next methodology, which is called multiple condition coverage. Write sufficient test cases such that all possible combinations of conditions, outcomes, in each decision, all points of entry are invoked at least once. Basically, what that's saying is the compiler expansion, everything, if you apply decision condition coverage to this flowchart, you would satisfy the definition of decision condition coverage. Okay? So the final exercise we'd like to do here is, and we already know that this doesn't cut it, right? Come up with, we're basically answering for the multiple condition cases. Come up with test cases to satisfy decision condition coverage for the actual expansion. Okay? So that's the final exercise. So let's spend like 5 minutes, something like that on now. It's about 23 after, so we're good timing to finish this and go to lunch about 2:30. I mean, 12:30. You can't wait that long, right? Or else you're going to be seeing signs like that with the black shrimp, right? In fact, I'm going to get a camera, take a picture of that post. I swear to God, I'm going to do that. Somewhere I'm going to use it during a class as entertainment or something. Of course, even with this one, try to minimize the number of test cases. You know? You can easily do 3 or 4 or 5, but get as minimum test cases as you can. almost fun. Right? Okay, somebody have any? Do we need lunch? What's the minimum number of test pieces? 4, right? Better, right? 3? Okay. Anybody do it with 2? I'll buy you lunch.
Yeah, that is the church.
Okay, so what's some test pieces? Numbers. Somebody else. Anybody? Yeah, number 2.
2 zero.
No?
0 1 0.
No?
And 3 1 2.
Okay, play computer. What's going to happen? This guy, where do we go? Yep. Where do we go? Yep. Where do we go? Yes? Okay. Test case number 2. No. No. And no, right? We got some legs missing here, and hopefully that does. Where do we go? Are we greater than 1? Yep. B is 0, no. Looking good. Equal to 2, nope. When we get down here, where do we go? So we're satisfied, okay? So got it. Now we go to lunch. No, not quite. One more. In fact, it's what been like Robert's been hinting at, and something that seems like something really strong we could apply. And it's called flow path combination. It's really strong. All possible combinations of flow paths based on all possible combinations of condition outcomes in each decision. And again, with the proper program definition here. So that's a total flow path based on the conditions and decisions. I mean, it's totally exhaustive. However, here's a comment, like for almost extreme cases, it may be an overkill. Hell of a lot of test cases, right? The other methodology is we come up with the most number of test cases for how many? 3, right? Hey, this guy cost you. You're gonna have to pay the fiddler on this one, right? Lots more test cases can involve flow combinations. But, well, let me describe what this is first. These are the values of the data here, and then these decisions go back to the original flow chart, you know? So, the true refers to, A greater than 1. The second thing is the B equals 0. The third is A equal to 2, and then X is greater than 1, you know? It just comes down here. Is that a lot of test cases? No. In fact, if this is a real-time program or something that's run over and over and over and over again, is this maybe a good idea? Sure, I've done that. You get a program that a lot of people are using everything, and it's not like infinite number of test cases and everything. This might be a darn good way of doing it, because you know it's going to do every condition and decision and all the flow paths, right? So it might be a good idea, but you got to use judgment. And general, you can't afford this. You gotta choose one of the other ones. And the guidelines we usually recommend is to do the multiple condition coverage. Right? But then based on time and money and stuff like that, you might have to choose like another one. Okay, some steps of white box collection is, determine your selection criteria, look at decisions, conditions, paths, and so forth. Make some judgments, in other words. How many paths are there and stuff, you like to look at it. Determine like the number of test cases like would be needed based upon the criterion. And then consider combinations of conditions, look for values, look for extreme cases, look for negatives, ones you wouldn't even thought about, boundary conditions like that. And then select the specific test case values input to accommodate the path flow selection criteria you choose. And of course look for completeness of correction, right? So that's good, right? But there's a disadvantage of the white box, They may not meet the specifications, right? You did all the flow path testing or white box criterion testing that you're doing. You can do it till the cow comes home, and the program may not still meet the specifications, because what you're concentrating on is the program and the paths involved, right? So that's